This is our next topic. In fuzzy quantities, how to calculate the expectation value of an operator. This is a new term, expectation value. We will explain it. So we have in the previous class we have discussed how fuzzy quantities appear in our in one of the previous classes. We have seen how fuzzy quantities appear in our experimental measurement. Okay. We have seen the example of a hydrogen atom in the ground state of energy. When we measure radial distance of the electron from the nucleus, in each trial of the measurement we get a different value. And when we get a different value in each trial of measurement, we call that physical quantity a fuzzy quantity or a dispersed quantity. Another name is dispersed quantity. So the value of the radial wave function is fuzzy or dispersed when the hydrogen atom is in a stationary state, not necessarily in the ground state of energy. Even though in the example we have discussed the ground state of energy, it can be any state of energy, any stationary state. So it is the position of the electron is fuzzy or dispersed. So here the fuzzy or dispersed quantity appear in our experimental measurement. Let us ask the question, when does a fuzzy quantity or a dispersed quantity appear in our calculation? Okay. Now, when we go back to the example of a hydrogen atom in the ground state of energy, this is the wave function of the hydrogen atom in the ground state of energy. Now, we are measuring the position of the electron, right? The important point is that this wave function is not an eigenstate of the position operator R. This is the position operator, the radial of the corresponding to the radial distance. So this ground state of energy of the hydrogen atom is not an eigenstate of position operator. So what? So if we measure a physical quantity in a state which is not an eigenstate of the corresponding operator, then the result of measurement will be a fuzzy quantity. Okay, result of measurement will be fuzzy. That is, in each trial of the measurement, we get a different value. Okay, so in the example of hydrogen atom in the ground state, when we measure the radial distance of the electron from the nucleus, we get a different value in each trial of measurement because this state is not an eigenstate of R. Instead of not an eigenstate, we often use this term, a general state. So the word a general state is simply another way of saying not an eigenstate. If some state is not an eigenstate of an operator, then we say that it's a general state of the operator. Okay, so this ground state of energy of the hydrogen atom is not an eigenstate of position operator. In other words, it's a general state of position operator. So whenever whenever the state of the system is not an eigenstate of the operator or a general state of the operator, then the measurement of the corresponding physical quantity will be, the result of measurement will be fuzzy, in the sense that in each trial of the measurement we get a different value. Okay, so here in the first half of our statement we talk about the state is not an eigenstate of the operator, but in the second half we talk about the experimental value. Okay, each trial of the measurement will give a different value. Let us try to combine, let's try to talk about the second half also in terms of calculation, right? So the question is, what are these different values that we obtain in each trial of the measurement? Okay, So let us consider a general point. Whenever we measure some physical quantity in some state of the system, right? It can be an eigenstate or it cannot be. It can be a general state. So whenever we measure a physical quantity in some state of the system, then the value that we obtained, values that we obtain in each trial of the measurement, okay, these are one of the eigenvalues of the corresponding operator. Okay, so we measure a physical quantity in some state of the system. So my point is this: the experimental values in each trial, experimental value, okay, in one trial we get one value, so the experimental value in each trial of measurement, okay, this is one of the eigenvalues in each trial of measurement of a physical quantity. Let us say this physical quantity, let us use the symbol A, capital A for that. It can be energy, it can be position. So the experimental value we obtain in each trial of measurement of a physical quantity A is one of the eigenvalues of the corresponding operator A cap, where A cap is the operator corresponding to the physical quantity A. Now, this is a very fundamental idea in quantum mechanics. Okay, we can see that the left hand side talks about the experimental measurement, the values that we obtain in experimental measurement, the results of our experimental measurement. The right hand side talks about a calculation, theoretical calculation. So, the experimental value we obtain in each trial of measurement of a physical quantity A, when the in some state of the system, I haven't talked about the state of the system, so it can be any state of the system. This will be equal to one of the eigenvalues of the corresponding operator A cap. This is a very fundamental idea. Now, with this idea, let us go back to our discussion of sharp and fuzzy quantities. Okay, in some cases, the state of the system in which we measure the physical quantity A, the state of the system can be one of the eigenstates of the corresponding operator A cap. We are measuring a physical quantity A in some state of the system. So in some cases, this state can be an eigenstate of, that is one possibility. It can be an eigenstate of the corresponding operator. Okay. So when it is an eigenstate of the corresponding operator, this point we have discussed in our previous classes. When the state of the system is an eigenstate of the corresponding operator A cap, what is the result of our measurement? Each trial of the measurement will give the same value. What is this value? It is the corresponding eigenvalue of the operator corresponding to that state. Okay, already we said that the state of the system is an eigenstate of the operator. Then corresponding to this eigenstate, there is an eigenvalue. Okay, that eigenvalue is the quantity that we will obtain in each trial of the measurement, and this we call a sharp quantity. So I can say that system is in an eigenstate of A. Okay, then what is the result of each trial? What we get is a sharp quantity. What is meant by this sharp quantity? it is the same eigenvalue in each trial. Remember that the experimental value that we obtain in each trial is one of the eigenvalues of the corresponding operator. If the system is in an eigenstate of A, okay, we get the same eigenvalue in each trial. Okay, this we call a sharp quantity. Maybe I should say this first. Okay. So we get this. If the system is in an eigenstate of A, we get the same eigenvalue in each trial, and this we call a sharp quantity. When we say that this physical quantity A is sharp, this is what we have underlined in one of our previous classes. A physical quantity is sharp in its own eigenstate. A physical quantity becomes sharp, that means each trial gives the same value when the system is in an eigenstate of the corresponding operator. Now we have added that. What is this value? It is the same eigenvalue in each trial. Okay. So this is the situation when system is in an eigenstate of A. But in other cases, okay, it can happen that system is not in an eigenstate of A. System is not in an eigenstate of A. In other words, system is in a general state of A. Now, in that case, what is the result of each trial? We get different eigenvalues in each trial. So, different eigenvalues in each trial. Different eigenvalue. Okay, in each trial we get one eigenvalue, different eigenvalue in each trial, and this we call a fuzzy quantity. So this is the idea. So in general, when the system is in any state, okay, the experimental value in each trial of measurement of a physical quantity A is one of the eigenvalues of the corresponding operator. Then there are two possibilities. In some cases, the system is in an eigenstate of A, then we get same eigenvalue in each trial, and this we call a sharp quantity. In other cases, the system is not in an eigenstate of A, or it is in a general state of A. Okay, then we get different eigenvalue in each trial. Okay, this we call a fuzzy quantity. We have seen the examples. We measure energy in the ground state of energy of hydrogen atom. So this psi 100. When we measure energy, what is the corresponding operator? Hamiltonian operator. This is an eigenstate of the Hamiltonian operator. Then each trial of measurement will give us the same eigenvalue, which is minus 13.6 electron volt, which is the corresponding eigenvalue. We say that the energy is sharp in the ground state of energy. In general, energy is a sharp quantity in any stationary state. Okay. Now, if we measure radial distance of the electron, okay, in the ground state of energy, this is not an eigenstate of the corresponding operator, the position operator. Then we get different eigenvalue in each trial. Okay, we say that the position is a fuzzy quantity in the ground state of energy. In general, position is a fuzzy quantity in any stationary state. Okay, so this is the idea. So we get a fuzzy quantity as the result of our calculation when the system is not in an eigenstate of the corresponding operator, the operator corresponding to the physical quantity that we are going to measure. Okay. Consider the example that we discussed before. The system is hydrogen atom in the ground state of energy, and the quantity we are going to measure is radial distance of the electron from the nucleus. We have seen this table in one of the previous classes. This is only one possible set of the result of 10 trials. Okay, doesn't mean that this we will get when we do the experiment, but this is one possible set. Okay, when we do the experiment, we may get another possible set. So in 10 trials, we get a set of values. We can see that in each trial, the value is different. Why? Now we know that the reason is that the position operator, the hydrogen atom in the ground state of energy, that is the state is psi 100. This is not an eigenstate of the position operator r cap. Okay, so if it is not an eigenstate, then in each trial we get a different eigenvalue. So these are different eigenvalues of the position operator. We call it, since in each trial we get a different eigenvalue, we call it a fuzzy quantity. Right. So one point is that we cannot predict beforehand what will be the result of a particular trial. Okay, for example, trial 1. We cannot predict beforehand what will be the result. Now we get 1.6A0, but we don't know beforehand. In trial 8, we don't know whether we will get this value. Okay, so we cannot predict beforehand what is the result of a particular trial. But what we can predict, that means when I say predict, what I mean is calculate. So, but what we can calculate is the probability of getting a particular eigenvalue as the result of our measurement. The probability of getting a particular eigenvalue as the result of our measurement. For example, we can calculate the probability of getting 1.6A0 as the result of our measurement. How much probability is there? How much probability is there for this one? Actually, the probability for getting this value is very low. So if we do some 10 trials or some 100 or 1000 trials, maybe this will appear only a very few times. So that means the probability will be very low. We cannot talk about all these probabilities in 10 trials. Okay, we can talk about probabilities only if the number of trials is very large. Okay. Since I cannot show the result of some 100 or 1000 trials, I am taking only a sample here, a very small set of a sample set. So the point is we can calculate, we can predict, that means we can calculate the probability of getting any eigenvalue as the result of our measurement. Earlier I mentioned that A0 is the most probable eigenvalue, most probable value. When the hydrogen atom is in the ground state and when we measure the radial distance of the electron from the nucleus, the most probable value will be A0. That means this has maximum probability. That is the meaning of that. When we do some 100 trials, this will appear maximum number of times. We can calculate the probability actually. So we can calculate the probability for each of these values and for other values also that doesn't appear in this particular data set. How do we do this calculation is another question that I am not going into now, but the point is that we can calculate the probability of each eigenvalue of the result of each. So even though we cannot predict beforehand which particular eigenvalue that we are going to obtain as a result of a particular trial, we can calculate the probability of getting any eigenvalue. If we can calculate the probability of getting any eigenvalue, then we can go on to calculate the average of all these trials. Okay. So we will come back to the question of average value a little bit later. For the time being, let us consider this question. What is the state of the system immediately after the measurement? We know that before the measurement of the radial distance of the electron, the state of the system is the ground state of energy of the hydrogen atom. What is the state immediately after the measurement? For example, consider our first trial. We get the result 1.6A0. So instead of going into the next member of the ensemble, remember that we do these measurements in an ensemble. For example, if we need to do 10 trials, we have an ensemble of 10 hydrogen atoms identically prepared in the ground state of energy, and we do one measurement in each member. Okay. Instead of that, if we want to find out what is the state of the system immediately after the measurement, what we do is we do the first trial on first member of the ensemble and we get this value. Then we repeat the measurement of radial distance of the electron in the same member of the ensemble, in the same system. We don't go to the next member of the ensemble. We repeat our measurement here. Then what we get is, we get the same value, 1.680. If you do the measurement a third time, again we get 1.680. Okay, so what does it mean? Initially it is in the ground state of energy of the hydrogen atom, but after the measurement of radial distance of the electron, let us say position, we get this value. If we repeat the measurement in the same member of the ensemble, in the same system, we get the same value. Suppose it is in the after this measurement, suppose it is in the ground state of energy, the state is the same. So let us say the state has not changed. If the state has not changed, we should not get the same value. If we continue to get the same, if we do a second measurement in the same system, we get this. A third measurement, we get this. A fourth measurement, we get this. It means that if the repeated measurements give the same value, it means that now the system is in the eigenstate. Eigenstate of which operator? Eigenstate of position operator. If it continues to remain in the ground state of energy, we should get something like this. Not necessarily these values, but in each trial we should get a different value, which is a different eigenvalue of the position operator. But after the first trial, okay, we get this value, and if we repeat the measurement in the same system, we continue to get the same value. If we do any number of trials in the same member of the ensemble, we continue to get the same eigenvalue, same value, 1.680. So it means that now the system has somehow come to the eigenstate of position operator corresponding to this eigenvalue. Okay, I can say that in trial 1, what happens is from the general state, okay, the system now changes to the eigenstate of position corresponding to this eigenvalue. Let me label it as, okay, let me use the symbol phi for the eigenstate of position, and corresponding to this eigenvalue, right, 1.680, let me say 1.680, let me label it like that. Remember that we can label an eigenstate in terms of the eigenvalue. So this is the eigenstate of position operator corresponding to the eigenvalue 1.680. So from the general state, the system changes to this eigenstate. What about trial 2? In trial 2, we get 1 point. So where do we do our trial 2? We go to the next member of the ensemble. Remember, we have 10 hydrogen atoms identically prepared in the ground state of energy. Trial 1 we have done in the first member of the ensemble. We get 1.680. Then we did some, when we do some repeated measurements in this first member, then we see that after trial 1, when we do repeat our measurement of position, we continue to get 1.680. It means that now it has come from the ground state of energy of the hydrogen atom to the eigenstate of position operator corresponding to the eigenvalue 1.680. Go to do trial 2. Trial 2 we do in the second member of the ensemble. Now this is in the ground state of energy of the hydrogen atom. So before the measurement it is in this one, ground state of energy of the hydrogen atom. We do the measurement of the position. What we get? We get 1.780. Now if we continue to do this measurement of position in the second member, after getting one value 1.780, if we repeat our measurement, we get again 1.780. A third time we get again 1.780. What does it mean? Now it means that now we get repeated measurement will give the same eigenvalue. It means that now it is in the eigenstate of position operator corresponding to the eigenvalue 1.780. So in the second trial what happens is the system moves from the general state to the eigenstate of position operator corresponding to the eigenvalue 1.780. In trial 3 we get In trial 3, we go to the third member of the ensemble, we measure the position. So initially, it is in the ground state of energy of the hydrogen atom before measurement. But after measurement, we get the value A0. If we want to check what is the state of immediately after the measurement, we can repeat this measurement in the third member of the ensemble. We get again A0, a third time. If you repeat again, we get again A0. Repeat again, we get again A0. So repeated trials gives the same value A0. It means that now the system is in the eigenstate of position operator corresponding to the eigenvalue A0. So what happens here? Initially, the system is not in an eigenstate of position operator, or we say it is in a general state of position operator. Okay, so this is a general state. Before measurement, the system is in a general state. Okay, but after the measurement, what happens? The system moves from the general state to one of the eigenstates of the position operator. So this is an eigenstate. Eigenstate of position operator. So in the first trial, it moves from the general state to the eigenstate corresponding to the eigenvalue 1.6A0. In the second trial, it moves from the general state to another eigenstate corresponding to the eigenvalue 1.7A0. In the third trial, it moves from the general state to yet another eigenstate corresponding to the eigenvalue A0. And this is again a fundamental result in quantum systems. We use a term, we say that in any measurement, if the initial state is a general state, then as a result of measurement, the general state collapses to one of the eigenstates of the corresponding operator. We use the term collapse. This is called a collapse of a wave function from the general state to an eigenstate. From the general state wave function psi100 to the eigenstate wave function corresponding to each eigenvalue. So the result of a measurement is collapse of a general state wave function to the eigenstate wave function, or a general state collapses to one of the eigenstate. This is just a word, collapse. It only means that there is a sudden change, okay, from the general state to one of the eigenstate. Okay. Again, I have just told that we cannot predict beforehand what is the result of each individual measurement. If the initial state is a general state, that means not an eigenstate of our operator, then we cannot predict beforehand the result of individual measurements. But we can predict the probability of getting each eigenvalue. Okay. In other words, we cannot predict beforehand to which eigenstate the collapse will take place. But we can predict clearly the probability of getting any eigenstate or probability of this collapse into one of the eigenstates. Okay, so this is, let us keep in mind that these are just two ways of stating the same thing. Okay, if the system is initially not not an eigenstate, not an eigenstate of the position operator, we get different eigenvalues. In each trial of the measurement, we get a different eigenvalue. Okay, we cannot predict beforehand which eigenvalue that we are going to get, but we can we can calculate the probability of getting any eigenvalue as the result of our measurement. There is in another language, in other words, we are saying that the system moves from the general state to one of the eigenstates. We cannot predict which of the eigenstates that the general state is going to collapse into, but we can calculate the probability of the collapse. Okay, it's another way of saying the same thing, that in each trial we are getting different eigenvalues. But the point is that immediately after the measurement, the system collapses to one of the eigenstates, and it remains in that eigenstate. Okay, that we can experimentally ensure, we can experimentally check, verify by doing repeated measurements on a single member of the ensemble. In the first trial, we get some value, some eigenvalue. Okay, we cannot predict beforehand which eigenvalue that we are going to get. It can be 1.680, 1.780, 2.480, any value. We can calculate the probability, but we cannot predict, we cannot say which one we will get in the first trial. But once we get a particular eigenvalue, if we repeat the measurement, we continue to get the same eigenvalue. It shows that now the system has somehow moved from the general state to this particular eigenstate, one of these eigenstates, and it remains in that eigenstate. And that change we call collapse. It's just a word. The point is that system somehow moves from the general state to one of the eigenstates. This is again a fundamental result in quantum mechanics. Okay. Let us consolidate a few points that we have discussed. When the system is not in an eigenstate of the operator corresponding to the physical quantity that we measure, okay, not in an eigenstate is often we rephrase as general state. Okay, so whenever we say the system is in a general state corresponding to an operator, we understand that it is not in the eigenstate of the operator. So in this situation, there are two features that we have to understand. One is each trial gives a different value in general, which is one of the eigenvalues of the operator. Okay, the result of each trial is one of the eigenvalues of the operator. We say that a physical quantity is fuzzy, or another word is dispersed in a general state. When the system is not in the eigenstate of the operator, the physical quantity is fuzzy or dispersed. That is, each trial gives a different eigenvalue of the operator. And second feature is immediately after the measurement, the general state collapses to one of the eigenstates. The general state collapses to one of the eigenstates of the operator and remains in that eigenstate. So immediately after the measurement, the general state collapses to one of the eigenstate and remains in that eigenstate. I should say not immediately after the measurement. The collapse takes place along with the measurement. Measurement causes the collapse of the state from the general state to the eigenstate, and immediately after the measurement, the system will be found in that eigenstate. It remains in that eigenstate. Okay, so these are the two features when the system is not in an eigenstate of the operator corresponding to the physical quantity that we are going to measure.